Okay, everybody, let's get started. We've got one of our own professors today, which is always lovely. Hugh Davies is currently an associate professor at the Occupational and Environmental Health at the UBC School of Population and Public Health. He has a PhD in interdisciplinary studies and MSc in occupational and environmental hygiene, and is certified by the American Board of Industrial Hygiene and Comprehensive Practice. He has studied the non-auditory effects of noise for over a decade, investigating its role in cardiovascular disease, childhood learning, birth outcomes, and chronic diseases such as rheumatoid arthritis and diabetes. His work has resulted in the first large-scale Canadian map of noise in Metro Vancouver. He is a member of the National Review Committee on the Health Effects of Noise from Wind Turbines, which I believe he's going to be discussing today. He is also a principal investigator in the Canadian Workplace Exposure Database Project and the president of the Canadian Association for Research on Work and Health. So welcome, Hugh.
That's right. I wasn't going to say anything till you all applauded. It's because I got this fancy microphone. Okay, yes, correct. Thank you, Sarah, for that introduction, and thank you all for being here. Indeed, I am going to talk about the work of this National Review Committee. When it announced its findings in March of last year, everyone across the country that had been on the review panel was primed with talking points and slides and media advice on how to deal with the avalanche of interest that we were going to get in this report. And I got exactly 0 calls from the media on this, although the situation is completely different on the other side of the country, and that's one of the things I'll talk about today, or will come out of the talk. But wind turbines, as you may or may not know, how many people are from Ontario here? And did you hear of anything about the wind turbine controversy while you were living there? It's a much bigger deal there. Wind turbines are a relatively new source of renewable energy, and like a lot of new things, they've generated a lot of concern, and one of those concerns is around the health impact, particularly from the noise from these turbines. So Health Canada reacted to this growing concern by launching this national review group. And so what I'll be presenting today is the findings of that group. No new data per se, although I will talk a little bit about Health Canada research study that they did in parallel to this, where they actually did go out and collect some new data from wind turbine sites and residents living near wind turbines in Ontario and PEI. So I'll talk a little bit about that. But primarily this is a review of the review. And why should BC people care? Well, I'll talk a little bit about that. BC is a growing market for wind turbines, so this is in a way a cautionary tale perhaps about how we can do things differently from Ontario and some other jurisdictions. So this is the review. I've got one copy left. I did have a little bit of interest. I have one copy left of the executive summary, but you can find this online if you go to the Council of the Canadian Academy's website. And just clearly, this was the work of a lot of people, including the expert panel themselves, and a large number of people at the Research Secretariat, including one UBC student, Leila Steiner, who helped produce some parts of the report. So, what's the issue? Well, since before 2000, there were really no wind turbines of any size, what we would call industrial wind turbines in Canada. And since then, in those last 15 years, we've come up to be ranked somewhere in the sort of 5th, 6th, 7th in the world in terms of capacity, and also in terms of growth per year. The increase is around 23% in capacity per year. So it's definitely a very quickly growing area of energy generation. We know that noise from other sources, environmental sources such as traffic, cars, planes, trains, are associated with adverse health effects. So there's some reason to believe, or not to disbelieve, that wind turbines themselves would not necessarily be the source of similar adverse health effects. And then there's a huge amount of anecdotal reporting of adverse health effects, and I'll talk a little bit about that. from people who live near them. And this is one of the main messages that we see in the community response, is that these wind turbines are causing poor health in humans, but also in animals that live close to wind turbines. And so you see scenes like this. This was a protest by rural Ontario residents in 2012. I don't know the exact location, but I'm guessing it's outside of the provincial legislature. Ontario had a very aggressive policy to try and increase wind turbine presence in the industry in Ontario. And so along with the potential health issues come a lot of sort of social justice issues. There's the existing relationship between these residents and the government. There's this issue of property devaluation. You see one of the signs there, wind turbines devalue homes. There's concerns about just the change in the environment, particularly the visual environment, and a feeling that there was a huge lack of information coming to the residents before these wind turbine companies came up and started setting up shop in their back garden. So today's talk, I'm going to go through the report in same sections, in sections it's actually written in. So I'm going to talk a little bit about wind turbines because they're a fascinating technology. And then I'll talk specifically about noise exposure from wind turbines and what distinguishes it from other sources such as trains, planes, and occupational noise. And then I'll talk a little bit about the review of the evidence for the health effects, and then talk about possible controls, how to reduce the impact of wind turbines, which is, as I say, perhaps useful as we move forward in British Columbia, and talk about future in terms of options and research and so forth. Okay, so has anyone been to the Grouse Mountain wind turbine and been on the tour? Oh, of course you would have. So hi. So this is one of the 5 operating installations in British Columbia at the moment. This is up on the top of Grouse Mountain. If you haven't noticed it yet, on any trip now leaving the UBC, you can look up and you'll actually see this. It's quite visible. This is downtown Vancouver. This is the top of Grouse Mountain. It's at the top of one of the chairlifts. And you can, for $19, go and visit this wind turbine. But it is an example of exactly what I'm going to talk about today. It's a large industrial wind turbine. It produces 500 kilowatts of power. This was the style of turbine that we want to look at because it's the most relevant to the growing market, as we'll see in a minute. So it's onshore. You've probably seen wind turbines offshore. Sorry. Yeah, you have seen wind turbines that are offshore. These are onshore. They have a horizontal shaft, that is, the blades are spinning in a vertical motion, and they are what's called an upwind rotor. So the rotor itself is in front of the nacelle, which contains all of the mechanical components. So this is a good example. What's different about it is this viewing deck. So the story behind this is that the CEO or the owner, I'm not sure which, of Grouse Mountain was in Italy buying ski lift equipment, and he saw the wind turbines there and decided this would be something that would suit Grouse Mountain's sort of economic development in the sense it's green energy. It fits with their idea of being a green company, but then to add some utility, why not add it as a tourist attraction? And so there is actually an elevator that goes up the middle of this wind turbine, and you can get out and have a look around. But as I say, that's the kind of wind turbine that we were studying in this review, and a good example. Now, to give you an idea of the size of these, because you've got a hint from the people, I think, in that previous diagram, but this schematic is of a wind turbine that's about the same size as the one on top of Grouse Mountain, and that is a 747 jumbo jet to scale. So the hub height, so the tower to the hub, which would be at the center of the rotor here, can be anywhere from 60 to almost 100 meters high. And then the rotor itself can be anywhere. In this case, this is a 70-meter rotor, but they can also be up to about 100 meters. So these are enormous mechanical devices, and there's reasons that they want them large. There's benefits to being large. But another way, if you're not an aeroplane person, another way you could think of this is if you laid one of these down in a football field, they would just about fit the length of the football field, but they'd actually spill out on both sides of a football field. So they are enormous. And to give you another idea, this is coming through time from the 1980s into the future. The one we're looking at there, is about an 80-meter hub height here. It'd be this one in the middle. The largest offshore facilities that we're looking at now, it would be something like this 125 meter. These are currently being used on offshore sites. So the ones that are in the ocean, this would, or in some body of water, are already at 125 meters. And yeah, there's proposal or plans for up to 250 meter high wind turbines. And then you add on to that the rotor height. So the benefits, of course, of being bigger is just the economy of scale and fewer of the individual units to have to maintain. But the other thing is that the wind, which obviously drives these things, is going to be more consistent and running at a higher velocity the higher you go. So you want to get these blades up into the consistent and stronger winds. And you can do that by increasing the height. Now, this is why Kay says we really have to get new projectors down here. So this is supposed to be a color graph. And on my screen, I can see some nice delineations. But what this shows is starting from, this is the number of wind turbines. And as you can see, we're over 5,000 wind turbines now in Canada. And these color gradations, as they go up, they're basically talking about the size of the wind turbine. So this is in megawatts. So you can see that the first wind turbines were less than 0.5 megawatts, 500 kilowatts. And then around 2003, they started to be replaced by these sort of zero or around up to sort of 1.5 megawatts. And they can now basically make the bulk of the capacity in Canada. But now we're seeing these 3 megawatts, as from about 2007, 2008, the 3 megawatts are now starting to add into the fleet. So it's they're just getting bigger and bigger as time goes by. This is an up-to-date infographic on the current installed capacity, and you can see where in Canada they are mostly concentrated. So Ontario by far has the biggest concentration of wind turbines, 4.3 megawatts, followed by Quebec, 3.2 megawatts. But every province pretty much has some wind turbine feeding into the grid. And in BC, right now we're at about a gigawatt, or 489 megawatts. The internationally, this is a little out of date. This is 2014, but it's not far out of date. Here we are down here about 8th or 9th place. I think we might have jumped up a place or two here. This shows us in terms of the overall capacity with respect to the rest of the world, with China and United States way out in front. And the blue, or the dark caps you can see on these, is the new capacity in that 1 year. And as I said, Canada, you can see, is disproportionately larger, and it's actually ranks very high in terms of the new capacity we're adding each year. So this is definitely something which is in a big growth phase. In terms of future plans, CANWEA, C-A-N-W-E-A, which is an acronym for the Canadian Wind Energy Association, their goal as an industry association is to have 20% of the national energy produced by wind by 2025, which would mean going a 6-fold increase from where we are now, 5 to 6-fold increase. So if they continue to plan and we maintain that plan, then we could be seeing very fast growth in the next few years. Okay, so I just wanted to talk a little bit about the details of a wind turbine. So this is at a site we visited in Ontario, Melanchthon, which is one of the big wind farms in southern Ontario. They're pretty simple. There's a foundation, a concrete foundation. Their footprint is actually pretty small. When they're being built, there's a lot of construction going on. So if this is a farmer's field, that you can see a utility road going up to it. But really, that's the extent of the footprint. A utility road that goes up to the base, and then the base is probably about the size of the center of this room. But every farming activity can go on right around it. So you can have cattle grazing or growth of grain and so on. Then there's the tower, which goes up to that hub we talked about. The nacelle here is where all the mechanics are. That's where the gear assembly is and the actual generator. And so that's one potential source of the noise that we're interested in because of the mechanics of the gearing and so forth. The rotor itself is a series, usually 3 in the modern turbines, of aerofoils, so just like an aeroplane wing, so that when wind hits them, they will turn because of the pressure difference and the camber on the blade. And they have a trailing or a leading edge, which is the edge that's just going to strike into the wind first, and a trailing edge, which is the back end of the wing, if you like. And we call the very end the blade tip, very original. And then, yeah, that's it. There's a staircase or a ladder that goes up, typically in the tower, for people to go up and do maintenance on them. They also are rotating so that they can rotate in and out of the wind. Usually they want to rotate into the wind. So that in itself is not a big deal, except when you think about the noise signal that's coming from this. You've got a blade turning in one direction, and then the whole thing is also turning, and then you've got the wind coming through it. It sets up quite a sort of complex environment in terms of the sound signals that are going to come off of it. In terms of the operation, wind turbines have what's called a cut-in and a cut-out wind speed. So they won't start until the wind reaches a certain speed, and that's so that they're not just they're not economical to run until the wind reaches a certain speed, and then they'll cut out when the wind gets too high, and that's to protect the mechanism inside. So typical range, I just wrote down one, is 3 meters per second to 25 meters per second. That's its operating range, and its optimum output. So the power curve is sort of asymptotic. The optimum wind speed is about 12.5 meters per second. Now that's 30 miles an hour. So that's not insignificant, which is again why it's better to have the blades up here where it's clear of all of the obstacles on the ground, which would slow the wind speed down. In terms of sighting, there are 3 main terms that you'll hear. So this is the offshore sighting, as I mentioned. Basically, this is, I think it's North Sea. I should have written it underneath, but anyway, you can see, can you see? It's a pretty grotty reproduction. But anyway, a very large number of these wind turbines, and these are all probably larger than the ones we've just been looking at. The offshore turbines are much larger. So that would be an offshore wind farm. This is Grouse Mountain, so you do get occasionally one turbine set by itself, but by far and large the more common sighting is like this one over here, the top right, and this is an onshore wind farm. And they do look kind of almost cute. You can see these things down in around Ellensburg, and it's a beautiful sight, and you see them like this initially, and then you get closer and closer and you realize how big they are. And I don't know if you noticed here, but here's a huge ranch house down here, the bottom. And then you get an idea, yeah. Then you get an idea of the scale we're talking about. These are absolutely enormous. Yeah, so there's a number of reasons for where they get sighted. The first one, of course, is they've got to have wind, and plenty of it, and it's got to be consistent. One of the complaints about wind energy is that it's inconsistent, that you can't count on it necessarily when you need it. And so people will say there'll always be a limited, because if there's no wind, you're not generating any power. So you need wind. You also need it to be close to the grid if you're going to get power onto the grid. That's another issue. But other than that, they can be sited pretty much anywhere, and you certainly see them on public land, on private land, on First Nations reserves, and so forth. Okay, So the noise, as I said, some noise comes from the mechanics in the nacelle, but it actually turns out that that's a small component of the overall noise source, a noise that you get from wind turbines. Most of the noise is coming from aerodynamic noise, and it's the blade itself and its interaction with the air as it moves. Okay, and most of that noise is coming from the turbulence that occurs not at the very tips of the blades, but near the tips of the blades themselves. And out on the tips, the speed of these blades is quite fast. So they're traveling around 200 miles an hour, the blades, once you get out to the tip. And as I say, of course, they're also in a very windy condition. The wind's constantly changing, and you can have complex wind shears where the wind at one end of the rotor is different from the other end of the rotor. So there's a number of things that feed into this, but most of the noise is coming from the blades themselves. The type of noise that you get is broadband, which we'll see in a minute, which means it contains many frequencies, although it can have some tonal aspects. In terms of the research that I'm going to talk about, as in a lot of situations, it's actually quite hard to do good measurement data and get a lot of it that's relevant, especially for health studies where you've got cohorts of people and their noise levels are changing all the time, and there's a lot of people. So a lot of noise data that we've used, and I'll probably talk about today, is actually modeled using deterministic models like CADNA-A, which is something we've used here to model traffic noise. I'm just going to go into a little more detail about three key aspects of the noise signal, and that's sound pressure level or amplitude, frequency or pitch, and then the temporal aspects, which are something that make noise from turbines not unique, but it's something that makes them, they have a signature sound, as you'll see. So this is a sound spectra for, again, a typical wind turbine that you might see in one of those Ontario wind farms. There's a lot of lines on here, but just you can focus really on just one of these for the purposes of this talk. And let's take that upper blue line. That's the octave band analysis. So on the x-axis, we've got the center frequencies on a log scale. So 10 hertz, 100 hertz, 1,000 hertz, 10,000 hertz. And this is a wind turbine that was measured at 70 meters from the wind turbine. Is running at its optimum speed. And so what you can see is that the noise, the sound pressure level drops as the pitch gets higher. Okay, so most of the energy is down in this the low frequencies down here. And one of the other thing is you can see it's largely broadband, that is, it's happening across all these different frequencies, but you do see these peaks in here. It's more obvious that these 1/3 octave band and smaller analyses, but you can see these tonal peaks occur to do with the speed that the speed of rotation of the rotor and other parts of the mechanics. The other thing that I want to point out now, because we'll see this again, this dotted line represents the human hearing threshold, or an average hearing threshold. So everything on the right-hand side over here would be considered audible to the average human. Like, we're all, who is the average human? Well, we'll talk about that in a minute, but everything on the left-hand side would be considered inaudible. So you can see that down here, even when you have very loud, low frequencies, 45, 50 decibels, which is what this potentially is producing, it's effectively inaudible. The average person is not going to hear those low frequency contributions. And up here, where it becomes audible, above 100 hertz, we're down around 30, 40 decibels. So 30 or 40 decibels, those of you that are taking Murray's class, is relatively quiet. It's certainly quieter than conversational tone, probably with sort of whisper tone. And I don't have a huge amount. I'll give you my personal observations. We went to one operating wind turbine farm, and it was supposedly a typical day. And the noise I would characterize as being pretty much like the rustling of leaves or something. It was a background noise. You could certainly hear them turning, but it was not, in my mind, obtrusive. Now, that is not saying, I want to state, that's not saying I'm on a particular camp here, whether they're a problem or not. We're scientists that went into this completely open minds, but if I certainly, my experience was very much in line with what you see here. Now, I say that because I'm going to play you a soundtrack in a minute, and I purposely put the volume up so that you can hear a different characteristic, but I don't want you thinking that that's what they sound like all the time. So that was one wind turbine. This is data from over 150 wind turbines in Japan, all superimposed on one another. These are 100 to the distance from them was 100 to 1,000 meters, and we'll see that that's an important sort of range because that's typically where you would see residences in that range. And they're 10-minute measurements taken during the night time. But you can see it's very similar to the last graph that I showed you, but this shows you many different sites. So it's sort of real-world data from a number of sites in Japan. Okay, now so that's amplitude and frequency. Now the other thing that makes these wind turbines very identifiable is what's called their whooshing or their thumping. As you can imagine, that turning of that blade in some directions, in some orientations, if you stand in a certain orientation or it turns and puts you in that orientation, you're actually getting air almost being pumped at you. And so what you get is this, what's called an amplitude modulation. So on the x-axis now we have time, and this is in seconds. And you can see that this, and also on the y-axis you have sound pressure level or amplitude. And what you can see is the sound pressure level has this rhythmic, cyclic, virtually once a second, 60 hertz, which happens to be the speed of the rotor, increase and decrease. So womp, womp, womp. And we got different kind of metrics on here, but you can look at all of them, especially the orange, which is the sound pressure level in sort of fast mode, so it's catching these peaks better. And you can see that the difference between the bottom of the peak and the top of the peak is about 3 decibels. That's typical. They can go from sort of 2, well actually nothing, up to 5 or 6 decibels routinely. And they're said to be audible, that you can detect this amplitude modulation when that difference is up above 2 decibels. In rare situations, or infrequently, you can get this effect called enhanced, and that difference can get up to 10 decibels, and then it would be quite remarkable. So now I'm going to just play you...
A smart pig is a highly advanced piece of technology that we run inside the pipeline to inspect it.
Sorry, you went... So as I say, this is enhanced, this is with the volume turned way up so that you can, I just want to give you a sense of that whooshing or thumping sound. This is the amplitude modulation. So it's very recognizable. And when we talk later about some of the health effects, particularly psychological health effects, the fact that you can pick this noise out from amongst many other potentially masking noises is important. Okay, so there's 10 minutes of this. If you haven't had enough, I can send you you can get more online. Sorry for that. Okay. Oh, I thought I'd do very well. Okay. So other factors affecting wind turbine noise, distance. Distance is important, as you know. Noise decays with distance for a number of reasons, but the further you are away, the quieter the signal is going to be in general terms. Wind speed, the faster the wind, the faster the turbine, and potentially the louder the noise. I talked about wind shear, that's the difference with wind at height. Can also add not only to the noise signal itself, but it can add in a twist in that if you are down low where there's little wind and little movement of, say, trees and bushes and lower airspeed, you've got less masking noise, whereas the wind turbine is going to be higher and creating more noise, so you've got a sort of double whammy. It's quiet where you are and even noisier because of the high wind shear and the high wind speed at height. Indoor and outdoor is an important factor for human health issues because the actual structure of the building itself will attenuate different frequencies at different rates, and so you tend to get an enhanced low frequency signal indoors because the higher frequencies are being attenuated. And then masking I've talked about a little bit. So certainly when it's windy enough to drive a wind turbine, the wind itself is generating broadband noise. Small amounts of traffic can also cause a masking effect. However, much like the sort of cocktail party effect, because once you're attuned to that signal and you can hear it, then you can hear it even when it's being partially masked by other sounds. A particular concern that's arisen from individuals affected by wind turbine placement is this issue around low frequency and infrasound. So just for definitions, low frequency noise is perhaps a grayer definition, but it's usually, and certainly in the report, we used a definition of less than 200 hertz. And infrasound, by definition, is the sound that is inaudible. And generally speaking, that's accepted to be around 20 hertz. And unless it's a very loud, and you saw that graph I showed, greater than 70 to 100 decibels, it's inaudible by the average person. Now, there's a fairly big sort of variability around that, so probably plus or minus 20 decibels if you take in a larger chunk of the population. However, rarely does the low frequency noise coming from these wind turbines ever get to that kind of range where you would actually get into this audible range for infrasound. But as I say, the low frequency is there, and as it can be enhanced indoors as the higher frequencies are attenuated. So it's definitely a problem, but a potential problem. Okay, so that was it for the acoustics and noise. I want to talk a little bit now about, or get into the health side of things. And I want to start by talking about the hearing, and sort of talk just a little bit more about hearing sensitivity and why there is maybe some of this variability. So I'm not going to go through the anatomy of the ear. That was more to introduce this section, although we will be talking not only about hearing and the hearing mechanism, but also about the vestibular system, because that actually, we did spend in the panel quite a bit of time talking about the possibility of a direct stimulation of the balance system in the body by sound. So this is just to speak again about this, these hearing thresholds. One of the issues that was raised and we were sensitive to is that a lot of people tend to use these average hearing thresholds. So we recognize that in actual fact there's a lot of variability around that. And that, for instance, this shows out 2 standard deviations from the average for hearing threshold, and you can see that it encompasses quite a range here from that's more like 85 decibels, even down here at 4 hertz, all the way up to 120. So when we say that this is inaudible at an average for an average person, it's certainly going to be audible for if you are one of the lucky people or unlucky people who have particularly sensitive hearing. So when it comes to hearing acuity and sensitivity, it's important to recognize that normal hearing itself has a large variance. some portion of the population, and it's not a small portion, probably around even as high as 10%, has what's called hyperacusis. And that means that they are just more sensitive to noise, or they hear noise more loudly than the average person. And not just within that 1 or 2 standard deviations, but in a way that is sort of pathological and a major problem to sort of everyday living. So that's another at-risk population. And then there's a group of people who have some kind of vestibular system abnormality. So the vestibular system are the semicircular canals, which help you keep your balance and orient you in space. And there are a number of issues that we thought could increase someone's susceptibility. So I've just listed some of them here. And I'll talk a little bit more about that when we talk about the health effects. And then we also looked a little bit into a fairly new theory that has sort of come out in the last few years. I think it's only been looked at really in animals, that the low frequency part of the cochlea, so getting towards the tip of the cochlea, may be more sensitive to infrasound than we originally thought. So we think that infrasounds can't be heard, and that actually this theory doesn't change that. But it appears that the tip of the cochlea actually generates all sorts of electrical potentials to infrasound, but they're not coming from the auditory part of the cochlea, but they're coming from another part of the cochlea. So the theory there is that simply saying, well, people can't hear infrasound is not the same as people aren't experiencing infrasound, and it's not saying that necessarily that the brain isn't interpreting those signals in some way that we don't yet understand. Okay, so the health review was very interesting. So we weren't asked to look at wind turbine noise and one single thing. We were asked to look at health, and so that's what we did. The team went out initially and just looked at and said, well, what are the health effects of been associated with wind turbines? And this is a bit of a sort of tongue-in-cheek infographic. There's a very polarized online debate about wind turbines. And again, I put this up really because it does kind of give you the idea of the breadth of things that the team, the initial list that they drew up of all the things that are health effects that had been at least anecdotally connected with wind turbines. And there were about 200 different discrete health effects. And so the first thing we had to do was, well, that we eliminated the effects on animals, we stuck to effects on humans, and then we grouped and we simplified, and we got it down to 32 different effects that we were going to look at. Okay, and they vary from what we ended up calling, dermal effects, respiratory effects, vestibular effects, nervous, and then of course cardiovascular, and a number of others. And I'm going to talk about just a few of those. I'm not going to go through every single one, but I'll talk about a few and introduce some of the complexities of this issue as I talk about them. But essentially, the strategy we employed was to do this initial review of everything from the web to legal decisions that have been brought before environmental review agencies to the scientific literature, just to generate this initial sort of schema that we would follow. And then we went back and did a proper scientific systematic lit review and a critical appraisal to come up with our evidence, which we kind of grouped the same as IARC in terms of, that's the International Agency on Research on Cancer, which was sufficient evidence, inadequate evidence, evidence against, and so forth. So I'm just going to go through some of these and as I say, talk about maybe 2 or 3 in detail. So the first one, and the one that's been most widely studied, is noise and annoyance. And one of the many definitions, the definition we used was a feeling of resentment, displeasure, comfort, or irritation. It's important that the definition be given and be clearly understood that this was considered a health effect. It's the most important health effect I'm going to talk about today, potentially. when Health Canada released their study about a year ago, they didn't do such a good a job on describing how they had defined annoyance, and there was a huge outcry that they had been basically trivialized the whole study. That the one, because I think CBC reported the one health effect Health Canada found was people get annoyed, and the way it was delivered really got people's backs up, that the whole thing was being trivialized. The opposite of that, we felt that annoyance, and that was the part that Lena Steiner that worked on here from UBC, is that annoyance is a very important health effect, and certainly in line with the WHO definition of health, which is complete well-being with respect to physical, psychological, and social factors. And so it's an important subject. Nobody wants to be chronically annoyed. It's probably a precursor to stress and other more serious health outcomes. So we felt there was very good evidence for an association between wind turbine noise and annoyance. It was consistent across several studies that we looked at. It was robust after we adjusted for confounders. It was consistent with data that we had from other studies in road traffic and air traffic and so on. It's biologically plausible, and we had an exposure response. So those are all really the things you want to see when you do a critical analysis of epi literature that would demonstrate an association. Interestingly, we found a number of effect modifiers, the researchers that did this work have found a number of effect modifiers. There is a known human trait that some people are more sensitive to noise than others, and certainly that was detected. But visual aspects, people who could see the wind turbines were more sensitive to the noise from wind turbines than those that couldn't see them. So this starts to tell you a little bit more about some of the important aspects around wind turbine design and placement. It's not all about the noise. There are other things which feed into community response. Amplitude modulation, that whooshing sound, was also important in terms of affecting the level of annoyance. The higher the amplitude modulation, the more annoyance that there was reported, and pitch or frequency, the lower the frequency, the higher the annoyance. These curves are pretty famous. They're at the basis of a lot of the health policy around noise abatement in Europe. Just if you look at the one on the left is fine. I'll describe that. So across the bottom you've got noise levels in decibels, and on the y-axis you've got percentage annoyed. And the road, rail, and air curves are the dotted lines. These are from years and years of data, meta-analysis, and what they show is with increasing noise from those transportation sources, you get increasing reported annoyance. And we've always known that the different sources gave different effects. So air noise at the same level, so at 55 decibels of air noise, aircraft noise, more people find that annoying than road, and more people find that annoying than rail. And that's thought to be to do with the noise signal itself. Not the noise is the same amplitude, but it's how it arrives at you, how the rise time of the noise, the predictability, and so on. But what you can see is that the data that was collected, and again, we didn't do this analysis, this was done by researchers combining a number of studies on wind turbines, and you can see that in actual fact, people find wind turbines even more annoying than the most annoying transportation sound that we've studied previously. So that was very interesting. Because of time, I'm not going to go into this in a lot of detail, but as I said, Health Canada not only sponsored this review, but they also undertook their own novel or new health study in Ontario and PEI at exactly the same time. And they recruited 1,200 odd homes. They took one adult from each home and subjected them to questionnaires and also objective measures of blood pressure, cortisol levels, heart rate, and then looked at those outcomes and against measured noise and distance from turbine. Now, because of the timing of this, we didn't feel comfortable in including these results in the review itself, because they literally came out about a month before we completed, but they are published now at the Internoise conference, and I'm expecting a peer-reviewed journal soon. So this is a bit of an odd graph. I think they'll fix it when it comes into the peer review, because down here they've got decibels as on the x-axis, and then percentage annoyed on the y-axis, and then they've got noises in blue, so that's this second line, and let's just focus on that. But what you can see is there seems to be a kind of threshold around this 30 to 35 decibels of noise, and after that you do see this dose response with increasing annoyance, with increasing noise. These other factors, of course, wouldn't be on a noise scale, but I think what they're actually, the x-axis also reflects distance, and so what you're also seeing is with decreasing distance or increasing noise, you see increasing annoyance from these other effects like blinking lights, which would be the aircraft avoidance lights, and visual effects and so on. These are more, this is another two annoyance graphs. Now this shows another very interesting thing that was very controversial when it came out, is that here we see our dose response curves again for a highly annoyed given the decibels during an 8 meter a second wind. So I think these are actually modeled noise levels, but the difference in response is quite different between PEI and Ontario. So the question, of course, there is what's going on. Why would Ontario residents respond differently when be asked about annoyance from wind turbines than those in PEI? Sleep disturbance was another one that was relatively well researched. However, and of course sleep disturbance has many different aspects to it: time to go to sleep, the number of awakenings, the overall length of your sleep, and so forth. But in general, there was inconsistent evidence for an association between wind turbine noise and sleep disturbance, partly because not only was there a connection with noise, but also with the levels of annoyance. So in some studies, people couldn't link sleep disturbance with the noise itself, but it was linked with the annoyance. And I've just shown you that the annoyance isn't necessarily totally related to the noise, so it's a bit hard to interpret. But there are certainly evidence from other studies, and I talked to the class last week about studies which show that even when people think they are accustomed to noise in their sleep and sleep through noise events, their body actually can still respond physiologically, which is very interesting. I think I'm going to skip the stress because I want to get on to towards the end of some important material at the end. Cardiovascular disease, this is of course something I've studied a lot. Generally speaking, there was inadequate evidence of an association. There were very few studies that were able to look at this except through self-reports, which are not particularly valid or reliable in this case. But then this is the results from the Health Canada study, where they did look at blood pressure, systolic and diastolic blood pressure and heart rate, and indeed they also found nothing when they looked at for associations between wind turbine noise at different levels and effects on cardiovascular disease. Now, hearing-related outcomes, we were able to confidently say that there was no link between wind turbine noise and hearing loss, but that was not unexpected given the levels of noise were so low at most of the wind turbine sites. And for tinnitus, which is something else that had been anecdotally associated with wind turbine noise, again there was there was no evidence of directly associating the two. But then tinnitus is, people don't really know what causes tinnitus in the first place anyway, and so we couldn't really do much better than to say there was inadequate evidence. This infrasound on the inner ear, I hinted about this issue around the possibility of direct impact on the vestibular system. And so we did have a otolaryngologist on the team, and it was fascinating. This is probably the most interesting part of the study from me, or the review for me. But we talked about this issue of the impact of the low frequency noise on the cochlea, and that it's the outer hair cells, which are not normally, they're not the inner hair cells are the ones that really react to the auditory system and generate the signal for the auditory nerve that goes to the auditory processing center of the brain. But the outer hair cells, which have a less direct role, seem to be the ones that are getting stimulated by these low frequency noises, which is probably why we don't hear them, because they're not part of the auditory pathway directly, but they are nevertheless generating a nerve signal. And it's just that we don't know what that nerve signal means. So there's speculation that maybe this is feeding into some of these vestibular problems that people report around wind turbines, that there's some mechanism here that we still don't understand, but it has something to do with the outer hair cells. On the other side, people say, well, even if that was the case, the levels in tests, the noise levels that they had to use to produce these signals was still around 100 decibels, which is way higher than the levels produced by wind turbines. I mentioned a couple of diseases of the vestibular system. There's Meniere's disease. There's superior canal dehiscence. So basically, people who have problems with their semicircular canals, like holes. Some people have holes which connect, either they're fused to the skull, or you can have Meniere's disease, which is a disease in which the pressure within the semicircular canals is dysfunctional. Those may make people more sensitive to some of these incoming stimulus. And so it's possible that those groups do represent a vulnerable subpopulation. So of all the other health effects we looked at, including metabolic diseases, cognitive outcomes, psychological health, there was just simply not enough studies. An odd study here, an odd study there. Many of them were not very high quality. And then for another group of diseases, there was simply no research to actually review. So these could certainly be considered areas for further research. I hesitantly put in this NB on wind turbine syndrome. So this is a constellation of many of those anecdotal health effects that I spoke of, which one physician who wrote a book called Wind Turbine Syndrome has grouped based on case studies that she's done as being a syndrome that she calls wind turbine syndrome, and that she claims is a specifically identifiable disease grouping associated with wind turbines. So we didn't actually look at it because no one's really studied it, but we also felt that we were looking at all of the individual health effects anyway, without having to deal with it as a complex. What we were able to do is sort of bring some of this information together to propose a mechanistic model. And again, it's a bit complicated to go through at this stage of the talk, but only these solid bars, these few solid bars here, down through here to annoyance, were where we felt there was any confident links. The dotted bars here linking sleep, and sleep with annoyance, and annoyance with sleep, and both of them with stress. You really have to read the report to see the complexity that you can get into here, because all of these things are so interrelated. But dotted lines means that the evidence was limited at best. Okay, so what can we do about them? Well, right now what we do about them is we have things called setbacks. So an example is in Ontario, if you're going to build a wind turbine and it's not on your property, if it's on your property you can put it wherever you like, but you must otherwise have it at least 550 meters from the nearest residence. And that is supposed to take into account noise, but also mechanical failures. These things do fall over, they catch fire, and in places like Ontario they'll actually throw ice off the blades, and there's flicker of shadows that can be a problem. More important for us is that some jurisdictions do have noise limits, and they're usually dependent on the speed, so they vary dependent on the speed. Up in Ontario, for instance, up to 51 decibels at 10 meters a second, and that takes into account part of this idea of masking. There are a lot of technological improvements. There's a basically continual improvement in the design. I won't go into that in a great detail, but safe to say that industry is continually trying to address this problem. And another, from a research perspective, but also from a technical perspective, there is now an effort to improve our measurement technique. I showed you a lot of things that were LEQs, so that's average speed, average exposures, and clearly that doesn't take into account those peaks that we saw for amplitude modulation, for example. So it's important that I think that scientists in general make sure that we're using the right metrics to inform future studies, including health studies. The big thing that is clear from the work we did, but also the work that's been done by a lot of other groups, is that the health effects are the health effects. Noise is noise, health effects are health effects. This hasn't got anything to do with real connections. But in terms of separating out what are some of these perhaps effect modifiers, the personal attitude to the government, the personal attitude to the wind companies, certainly the visual citing of these things, a lot of it could be dealt with by better environmental and health impact assessments. And there's a lot of literature out there that shows that early and meaningful community engagement can go a huge way to reducing a lot of the problems that we see. And so there's some great case studies out of Europe, France and Germany that contrast different approaches. And what you see is where you get a community that's vested in some way, that it's either they're in control or they buy shares, they get to place the wind turbines, they get to decide when they're turned on and when they're turned off, that a lot of these problems actually disappear. So just very quickly end up with BC. I checked with the Environmental Impact Assessment website this morning. There are about 14 or 15 impact assessments that are either completed or are underway in some stage. These are the most, the yellow ones are the operational sites. So you can see that there's a clustering up here in the Peace Country. There's Grouse Mountains down here in Vancouver, and there's a big wind farm on the tip of Vancouver Island. In red, we've got sites under construction in Kelowna. That'll be the first ones in the interior, and another one up here in the Peace District. And then out here is the first ever offshore in the Hecate Strait, which is one of the windiest places on Earth. And I think that that's slowly moving ahead. A lot of this will depend on the politics and the economics. So if we get an NDP government in a year, for instance, John Horgan's gone on record as saying that he's going to support wind power. So that could be where we're going. I'm going to skip the conclusions because I'm almost done, and I'll just take any questions. I apologize for running over a bit.
Okay, we probably have time for one question, so who wants to be the lucky asker?
I'll be around for a little while afterwards.
Wow. Okay.
Interesting. So I haven't been up in the wind turbine up at Grouse Mountain here,
Yeah.
but I'd imagine that the health effect, the exposure wouldn't cast any huge negative health effects on the tourists who go there for a short duration. However, there's got to be an operator, and that operator is there for hours on end, I would imagine, exposed to the low frequency sound on an occupational basis.
Yeah.
So are you aware of any of such?
Yeah, well,
data?
no, these things, first of all, there's probably not an operator. They don't require any, they're completely remote. Whole wind farm generally only employs a relatively small group of people, maybe 4 or 5 people. No, they don't require any on-site operators.
But when you have tourists going up and down.
Oh, sorry, for the tourists, that's
yes,
true, yeah.
Yeah.
No, well, let's say, maybe I didn't make it clear enough, the low frequency noise is actually, even at the base of these turbines, so when you're right up close, the low frequency signal is not considered a health hazard in itself. Yeah,
Thank you.
Okay, one last question.
Chris?
This may be impossible, but ideally you'd want a blind study or double-blind study. Is it possible to assess what people think of these turbines when they don't know whether they're on or not?
Right. So a couple of the studies, there have been studies that have actually This has happened accidentally. We've had people have reported problems when wind turbines actually weren't even running, and but it is very, very difficult to do that. The Health Canada study, for instance, they kind of masked their study in a way that they included people that were very close to wind turbines, but they went up to 10 kilometers away, and they told them it was a study that was generally about sort of environmental issues. So they tried as much as they could to avoid asking directly, this is a study about wind turbines. You could certainly do lab studies on populations that did not have prior experience with wind turbines, but there's very, very little of that done. But yeah, ideally you would be able to do blinded studies. The big problem here, and some of the slides I skipped, is if you're going to do future health studies, it's going to be very challenging because you don't have very large populations, so you're going to always have small sample sizes, and a lot of these effects we're talking about are rare, so you need a very large cohort to be able to pick them up. Yeah.
Okay, thanks very much, everybody, and enjoy your reading break.